In this video, we'll take a look at in detail the review solutions for those equations of lines and planes test. And so in the multiple choice, we'll start with the first question. We're asked to find a vector equation of a line passing through the points 3, 8, and 7, 12. Now, for a vector equation, we need two things. We need the position vector of a specific point on the line, and we have 3, 8, and 7, 12, so we have two of those. We only need one. The reason we have two is because we need to find a direction vector. So to find the direction vector, we find the vector between these, and we can use any multiple of that. So to find the vector between them, we subtract the coordinates. So 7 minus 3 here, and 12 minus 8 here, so that's the vector 4, 4. Now we can use 4, 4 or any multiple. So if you divide both of those by 4, you'll actually get the vector 1, 1. And so that's the one that's actually used in the answer here. I could have put 4, 4 there, or 2, 2, or 10, 10. Any multiple that would do. And this could be 3, 8, or I could have put 7, 12 there as well. So that's why B is the correct answer for number 1. Notice that A is not correct. It's actually got them switched. This is where the point should be, and you see this is where the directions are actually switched. So if we put the 3, 8 here and the 4, 4 there, that actually would be a correct answer as well. And the E one here is not correct because although 3, 8 is the position vector of a specific point on the line, 7, 12 is not a direction vector. It's just another point on the line. For number 2, you're asked which of the following points is on this line. So you start substituting in the coordinates in place of x, y, and z, and you find the one that makes all of these three ratios the same. And D is the correct one. So if we put negative 1 in place of x, negative 1 minus 5 over negative 3 works out to positive 2. If we put the 9 in place of y, 9 minus 7 is also 2. And if we put 6 in place of z here, 6 plus 4 is 10 divided by 5 is 2. So notice that that is the one point, actually none of the other ones make the same thing in all three, is that satisfies the equation of the line. So D is the correct answer for number 2. For number 3, we're asked for the direction vector of this line. And remember, when you see something like y plus 3, in the symmetric equation, and this is not true symmetric form, the denominator is 1. So the x component would be 5, the y component would be 1, but notice there's a comma and then z equals 8, and so that implies, and this is actually the parametric equation for z, it's z equals 8 plus 0t, so 0 is the direction vector for z, or the direction component. So it would be 5, 1, 0, which is answer A here. For the next question, number 4, we're asked which of the following points is on this plane. And well, it says R because there's more than one of them, but there's only one that's actually on the plane. And the answer here is B. And the way you determine, or probably the easiest way to determine if it's on the plane, is start substituting in the coordinates 1, 2, 4 in this case in place of x, y, and z. So we put 1 in place of x, so it's 2 times 1, minus 5 times the y, which is 2, so that's minus 5 times 2, and 4 is the z coordinate, so 3 times 4 next, and then of course minus the 4. So 2 times 1 is 2, minus 10, plus 12, and then minus 4, that does equal 0. So that point does satisfy the equation. To demonstrate a point that doesn't, and that's what this is over here, for example, C is not. So if we put 0, 1, and negative 3 in place of x, y, and z, 2 times 0, of course, is 0. Negative 5 times 1 is negative 5, and then that would be minus 9 minus 4. That works out to minus 18. You see, it's supposed to equal 0 because it's a 0 on the right side of that equation. So that's why C is not on the plane, and of course also A and D are not as well. For number 5, two planes that are parallel and distinct, and this is what parallel and distinct looks like. They're two planes that are parallel and do not ever touch. That's what distinct means. They share no common points. They have parallel normal vectors. So here's examples of the normal vectors. That's the normal vector for the top plane, and that's the normal vector for the bottom plane. So if the planes are parallel, these normal vectors are also parallel. So that's why A would be the correct answer for number 5. Of course, they can't be coplanar because that's not what distinct means. Distinct means they do not touch at all. And if they do not touch at all, they cannot intersect in one point or more than 2 points. And they would have to always be the same distance apart. That's what parallel means. So that's why A is the only correct answer for number 5. For number 6, which of the following are vector equations of the plane through these 3 points? Through this point and containing these 2 vectors. These are not vectors, that's a point. Notice the convention I'm using here. The round brackets actually means a point. The square brackets refers to a vector. And so if we want the vector equation, we need the position vector of a specific point on the plane. So that's why the 6, 0, negative 2 is first. Now, notice I've written this as a vector. And that's because when I say the position vector of a specific point on the plane, it's the vector that goes from 0, 0, 0, the origin, to that point. So we would actually call it the vector 0, 6, 0, negative 2. And plus then parameters, S, I'll call them S and T, times each of these vectors. We don't call them direction vectors, they're vectors in the plane, because a plane is 2-dimensional, whereas a line is 1-dimensional, so it has a direction vector. So that's why B is the only correct answer for number 6. A, for example, isn't, because the 3, negative 4, 5 is a vector in the plane. It's not a position vector of a point in the plane. And of course, the same idea. This one actually is okay here. But, this one is not okay. Notice that the signs in the point have been switched. You can do that with a vector. That's okay. But you can't do that with a point. If 6, 0, negative 2 is on the plane, that does not mean that negative 6, 0, positive 2 is also on the plane. I suppose it's possible, but you're certainly not guaranteed that that's the case. Last question in the multiple choice, number 7 here. The lines, these lines are, and you're asked whether they're parallel, coincident, skew, or intersecting, or none of the above. And so, if you look at the direction vectors, these lines, 3, 0, 2 and 6, 0, 4 are multiples because 2 times that vector is equal to 6, 0, 4. So they are at least parallel. Okay, they could be coincident because if they're coincident lines are also parallel because of the same line. They certainly cannot be skew because they have direction vectors that are parallel. So C is not an option here. And actually D isn't either. Coincident actually would mean, I suppose, that they would be intersecting, but they'd be intersecting in every point of the lines. And that's not normally what we call intersecting. So to determine whether they are actually just parallel or they are the same line, that's what coincident means. Check and see if a point that's on this line is also on this line, or vice versa. And so that's what I said here. So, however, they could be the same line, which means coincident. So is a random point that's on the first line also on the second? So I'm going to check this point here, 2, 3, negative 1. That's the position vector of a specific point on the line. So I'm going to see, is that on the second line? Well, so this 2 here, the x component, would equal, and I'm going to set it equal to the parametric equation for x in this, which would be 4 plus 6t. So 2 equals 4 plus 6t. If you take 4 away from both sides, we get 6t equals negative 2, and divide out the 6, and you get t is, negative 2 6, or negative 1/3. So does negative 1/3, if we put negative 1/3 in here, does it also generate the 3 for y, or the negative 1 for z? And it doesn't, because the parametric equation for y here would be y equals negative 1 plus 0t. So y is actually negative 1 for every single point on this line. And that y coordinate right there, is not negative 1. So t equals negative 1/3 does not generate the y coordinate of 3 from that line. So that point is on this line, but it's not on this one. So that means that the two lines would have to be parallel and distinct. So they're just parallel lines. Part 2. In the first question, we're asked to find parametric, vector, and symmetric equations for the line through the points 6, negative 2, 0, and 5, 3, 1. And then we're also asked to find 2 points on the line other than those 2 points. So if these are 2 points on the line, we need to find a direction vector for each of these kinds of equations. So we would subtract the coordinates. So 6 minus, or actually I did 5 minus 6 is negative 1. 3 minus negative 2 is 5. And 1 minus 0 is 1. Now, if you subtract in the other order and got 1, -5, -1, that's fine. There's nothing wrong with that at all. Okay, so that's the direction vector that I am going to use, though. So here's I've given two possibilities for each of these. Here's a possible set of parametric equations. So notice I'm using 6, -2, 0 for the point here. So we would go 6 minus t, and then -2 plus 5t. And now the z coordinate here is 0, so it'd be 0 plus t, or just t for the last one. If you use, instead of that point, if you use 5, 3, 1, then it's 5, 3, 1 at the beginning instead of 6, -2, 0, and it's still -t, 5t, and t, -t, 5t, and t at the end. So that's two possible parametric sets of parametric equations. To write the vector equations, here's my point, position vector of a point on the line, and in this one I've used the 5, 3, 1 instead, plus t times the direction vector. So there's two possible vector equations. For symmetric, similar idea. So it would be, for this one, and it would be x minus 6 over -1 equals y minus -2, same as y plus 2 over 5, there. And z minus 0, which is just z, over 1, so we just write z. If we use this one to write the symmetric equations, we would go x minus 5 over -1 equals y minus 3 over the 5 equals z minus 1 over the 1, so which is just z minus 1. Now, if you make sure in your symmetric equations that you leave these in this form. For example, if it looked like it was convenient to multiply top and bottom by -1, for example, if you multiply top and bottom of this by -1, this would change into 5 minus x over 1, but that's not correct symmetric form, so don't do that. Leave it in this form. To find two other points, substitute non-trivial values in place of t. Non-trivial means not 0. You see, if I put 0 in place of t here, I'll actually generate the point 6, -2, 0, and that's that point there. You're asked to find 2 points other than these two. So if I put 2 in place of, and I use this first set to find both my points. If I put 2 in place, so 6 minus 2 would be 4 for x. If I put 2 in there, that's 10 minus 2 is 8. And of course 2 in place of t, then z's 2. And so the point 4, 8, 2 is a point on this line. Next I'll put 3 in. So 6 minus 3 is 3. Put 3 in here, so 5 times 3 is 15, minus 2 is 13, and put 3 in place of t, so the z value is 3. So 3, 13, 3 is a point on this line. Now you can put other values. I actually wrote several examples here. If you use different t values, all from the first set of equations. Of course, not necessarily the same t values in this one would generate the same points. But of course, they should still be on the line. For number 2, you're asked to determine vector and Cartesian. Cartesian and scalar mean the same thing. Equations of the plane contain the points 2, -1, 0, 0, 3, 1, and 4, 2, 1. So in order to find vector equations, and we need them to find Cartesian as well, you need a pair of vectors that are parallel to the plane. So find vectors between pairs of points. So for example, the vector between A and B. So we go 0 minus 2, which is -2. 3 minus -1, same as 3 plus 1 makes 4. And 1 take away 0, of course, is 1. So that's the vector AB. So we could do AC as well. So 4 minus 2, 2 minus -1, and 1 minus 0, and we get the 2, 3, 1 vector. Now you could also do BC or CB. That would be fine. I put it in red here because I didn't use it, although you could use that in the calculation instead of one of the first two vectors. So in order to write out the vector equation, I'll talk about that one first, and then we'll get into the Cartesian. The position vector of a specific point on the plane. So I used 2, -1, 0, but you could have just as easily put 0, 3, 1 or 4, 2, 1 at the beginning. Either would be fine. And so s, the parameter s times one of the vectors in the plane, plus t times another vector in the plane. And again, you could have used this 4, -1, 0 in place of either of these. Not both, of course, but either of them. To find Cartesian equations, you need to find a vector normal or perpendicular to the plane. So I took the cross product of these because basically what this looks like is here's the plane, and so let's say that's the vector AB, and this is the vector AC. So the cross product is a vector perpendicular to both of those. And so that's my normal vector because this should be a right angle and this also should be a right angle. So this is the like the AB vector, and this is the AC vector here. And so when I take the cross product, I'm going to get a normal vector to the plane, which is what I need for my Cartesian plane. So that's why I'm doing cross product here. So to do cross product, and there's lots of different ways to do it, I use this to calculate it. So I start with the y components to write 4, 1, negative 2, 4, 4, 1, negative 2, 4, and taking the cross product of that with AC, so 3, 1, 2, 3. Kind of looks like an order, 3, 1, 2, 3. And so we go 4 times 1 is 4, minus 3, this product is 3, so 4 minus 3 is going to give us x. This would be 2, now minus negative 2 is 2 plus 2, and that would be negative 6, subtract 8. So 4 minus 3 is 1, 2 plus 2 is 4, and negative 6 minus 8 is negative 14. So that's the normal vector for the plane. Those are the coefficients of x, y, and z in the Cartesian or scalar equation. So it's 1, 4, negative 14. So 1, 4, negative 14 are the coefficients of x, y, and z. We need just to find the constant d. And so I substituted the a point in, the 2, negative 1, 0 point. So 2 goes here, negative 1 in place of y, and 0 in place of z. And so this would be 2 minus 4 minus 14. Of course, that's 0. The 14's gone, sorry. So 2 minus 4 plus d, so d works out to be 2, because it'd be negative 2 plus d is 0, so d would have to be positive 2. Over here, I showed what the calculation looked like if you used the 0, 3, 1 vector instead of this one. So if we put 0, 3, and 1, 0, 3, 1 in place of x, y, and z. So that would be 12 minus 14, which is negative 2 plus d is 0, so d is still positive 2. You get the same value no matter which point. Of course, if you use 4, 2, 1, you get the same value for d. You have to, because it's another point on the plane. So putting that 2 in place of d, we get x plus 4y minus 14z plus 2 equals 0 is a Cartesian or scalar equation. So flipping over to the third question. Find parametric equations of a line through that point and perpendicular to this plane. Well, if that's the plane, then 2, 1, negative 7 should be a vector perpendicular to the plane. The line we're looking for is supposed to be perpendicular to the plane. So since the line we're looking for is perpendicular to the plane and that normal vector is also perpendicular to the plane, then the line goes like this. And so that line perpendicular to the plane would have to be parallel to the normal vector. And so I can use that 2, 1, negative 7 as a direction vector for this perpendicular line, 2, 1, negative 7, and it's supposed to go through the point 4, negative 3, 5, so that would be the constant at the beginning of the parametric equation. So that's why that's a possible set of parametric equations for this particular line. For number 4, it says determine whether the following pairs of planes are parallel and distinct, coincident, which means they're the same, perpendicular, or none of the above. And explain your reasoning. So here's the two planes, and so notice the normal vectors are 2, 3, 8, negative 8, sorry, and 6, 9, negative 24. Notice if I multiply this normal by 3, I get this normal. So 3 times this would be 6, 9, and negative 8 times 3, of course, negative 24. So the normal vectors are multiples, which means that the planes are parallel. Now they could be the same plane. To determine whether that's the case or not, you look at the entire equations. This normal times 3 is this normal, but notice the constant here. Well, I've got the constant written on the left in this one, on the right in this one, but if I took the 4 over to this side, it'd be negative 4. If you multiply that by 3, sorry, it's the same 3 you multiply here, negative 4 times 3 is not equal to 10. So the entire equations are not multiples. So that would mean that the second plane is not a complete multiple of the first. So they're parallel, but they're parallel and distinct. They're not the same plane. If, for example, that was a 4 and I had a plus 12 here equals 0, then they would actually be the same plane because they would be complete multiples of one another. Okay, so that's the case for number 4. They're parallel and distinct. For B, we're given these two planes. The normal vectors are 3, 5, negative 8, and 2, 1, 4. They certainly aren't multiples. Okay, but perhaps they're perpendicular. So if they're not multiples, we know that neither of these two are the case, but they could be perpendicular. So you check that with the dot product. You take the dot product of these, because if the planes are perpendicular, then their normals would be perpendicular. It would actually look like this. So let's say that's one plane, and let's say this is another plane that's perpendicular to it. Okay, kind of hard to draw that, but the normal for this one would look like that, and the normal for this one would be perpendicular to it. So if the planes were perpendicular, then the normal should also be perpendicular. So the dot product of n3 and n4, so 3 times 2 is 6, plus 5 times 1 is 5, plus negative 8 times 4 is negative 32, and that adds to negative 21, which is not 0. It would only be 0 if they were perpendicular, so the planes are also not perpendicular, so it would be a none of these one. For question number 5, it says determine the points of intersection of this line and this plane. To find the points of intersection, put your line in parametric form. That's just one of the ways to do it. So the parametric equations of this line would be 3 minus 3t for x. Remember, it's x or y or z minus the number in this case, the coordinate of the point on the line. Y would equal 8 plus 5t, and there's a comma, z equals 4. So that's actually the parametric equation right there, so z equals 4. So we substitute these in place of x, y, and z in the planes equation. So here's the planes equation. So 3 minus 3t goes there. 8 plus 5t goes in place of y, and 4 goes in place of z. And so we distribute the 7 in, be 21 minus 21t, the negative 2 in, so negative 16 minus 10t, and then plus 4 minus 71 equals 0. So combining like terms, those two t terms add to negative 31, and the constants, 21, negative 16, plus 4 minus 71 is negative 62. So when we bring it over to the right side, it'd be positive 62. Divide out the negative 31, you get t is negative 2. So t equals negative 2 is the value that generates the point that's on this line that's also on this plane. So we put negative 2 in place of t here. And of course, there is no t in the z equals 4 one. And so that's supposed to be an equal sign right there. Maybe we'll fix that. Or there's supposed to be an equal sign there. 8 minus 10, of course, would equal negative 2. So negative 2 would be the y coordinate there. So the point 9, negative 2, 4 is the point that plane uniquely intersects, that line intersects the plane. I use the word uniquely here. Unique means there's only one. So there's only one place where that line intersects the plane. And just to give you a visual of what it would look like, if this is the plane, then here's the line here. It's coming down and it crosses in one point, and I guess you could see it go at the other side. So this is the 1 point right here. That point would be the 9, negative 2, 4 point. On to question number 6, and there's two parts here. These are two where you've given 3 planes and asked to find out where and or how they intersect. Now, a couple of instructions here. If the solution is infinite, and that might mean that the planes are all the same or the planes intersect in a line. Okay, there's a couple of scenarios for that. You're asked to also find one particular solution, which is an example of a point that is on all of the planes. So if there's a line of intersection, then you just choose a random point in that line, and that's a point that's on all of the planes. So make sure you describe the type of solution, unique, there's no solution, infinite solution, and make sure on the test you show all of your work. You can use a calculator to check your work, but all the steps have to be shown here to get full marks. So this is the question for A, and the first thing I would do is take all these constants to the right side. So this becomes 3, this becomes -7, and -9 on the right. And I'll call those equations 1, 2, and 3, or planes 1, 2, and 3. And so I'm going to eliminate, now I see these negative z's here. And so right away that tells me if I'm using elimination to get rid of z's, then that makes that fairly convenient because I don't have to worry about multiplying either of those by a constant. I can just simply subtract them and get rid of the z's. So maybe I'll choose another pair because I've got to do it twice. I need two equations with the same variable eliminated. So I'm going to choose the first and second one to eliminate z. So I'm going to leave the first equation alone, that one here, and I'll multiply this one by 5. I guess I could also multiply by -5. Either would be good. So I'm going to multiply that equation by 5. So that would be 15x plus 20y minus 5z, and the equals -35. And so notice the z's are opposite, so we would add. So x and 15x is 16x. Negative 3y plus 20y is positive 17y, and the z's are opposite, so they add to 0. 3 and -35 add to -32. So there's an equation that has z eliminated. So again, back to 2 and 3, I can just not worry about multiplying them by anything at all. Just take equations 2 and 3. These two are the same two that are here, and subtract them because the z's are exactly the same. And so 3x minus 4x would be -1x, 4y minus 2y is 2y, the z subtract to 0. And -7, take away -9, same as -7 plus 9, which would be 2. So notice equations 4 and 5 both have z eliminated, so they just have x and y. And so we can take them, I'll move this up a little bit more, and I'm going to choose to eliminate x. So I want to make this 16x and this -1x are the same or opposites. So I'll leave equation 4 alone, and I'm going to multiply this one by 16, and that'll make that those x terms opposites. And so 16 times this is -16x, 16 times this would be 32y, and 16 times 2 is 32. And so when I add, because the x terms are opposites, 17y and 32y is 49y, and lo and behold, the constants are actually opposites as well. -32 and 32 add to 0. So when I divide it to 49, I get y equals 0. Okay, so I have a single value for y, so right now it appears as though I'm going to have a unique point where these three planes intersect, and the y-coordinate should be 0. And so now there is the second one actually involves when there's equation of a line, and we'll get into how that occurs and why. So y equals 0, so I'm going to put 0 into one of the equations up here, either 4 or 5 that has just x and y's, because I know what y is 0, so I can now find x. So I'm going to use equation 5, this one here, and I'm going to put 0 in place of y. So of course 2 times 0 is 0, and so we'd have -x equals 2, so x is -2. And just like I got a unique value for y, I should get a unique value for x, so the x-coordinate of this point of intersection is -2. So I'm going to go back up to the very first equation, this one right here, and I'm going to substitute my -2 for x and 0 for y into the first equation. So -2 goes in place of x, 0 for y. Of course, that's 0. So we have -2 plus 5z equals 3. If you add 2 to both sides, you get 5z equals 5. Divide it to 5, and you get 1. So the three planes intersect uniquely, so there's me describing how they intersect. They intersect in one point only, at the point -2, 0, and 1. And so that's number 6a. For 6b here, again, I have the constants on the left, and if they are, then I'll take them all over to the right, so it become 1, 2, 3. And I'll call them equations 1, 2, 3. And so I'm going to start by eliminating x from the first and third. Notice this equation doesn't have an x. So if I take the first and third and eliminate x, then I will all of a sudden right away have two equations that just have y and z, because I already have one that doesn't have an x in it. That's number 2 here. So here's the first equation, and here's the third one. And of course, there is another way to do this too. You of course could notice that there's no y in this. So you could eliminate y from those two and have equations that just have x and z. That's another option too. But I'm eliminating x from the first and third. So the y-axes are the same, so I would subtract. Negative y, now there's no y's here, so negative y minus 0 is negative y. Z minus 2z is negative 1z, and 1 minus 3 is negative 2. Now, if you notice that all the coefficients are negative, so if you multiply both sides by negative 1, you get y plus z equals 2. And notice that that's actually, so this is actually a linear combination of the first and third plane. Notice it actually gives you the second plane. And so that means right away, if two of the planes, like a linear combination of them, and it doesn't have to be just an adding multiple or subtracting multiple. It could be like 2 times the first plane minus 5 times the second plane. If that gives you one of the other planes, then that means that there's an infinite solution. They intersect in a line. We can see that certainly the normals are not all multiples, so these planes are not all parallel. But the fact that one of them is a multiple of two others, a linear combination, means that they intersect in a line. So that's how you know they intersect in a line. So that's what this point is saying here. Now, so to find the equation of this line of intersection, I could let z be t. It would be convenient to let y be t here as well. You actually have two fairly convenient options, and that's because the coefficients of y and z are both 1. So when you're making that choice, choose one that has a coefficient of 1, if there is one, and that's the most convenient way to do it. It's not always possible, but that often is the case. So I'm going to put t in place of, so here's my y plus z equals 2. I'm going to put t in place of z and solve for y. So we bring the t over, and y would be equal to 2 minus t. So that's the parametric equation for y in this line of intersection. So now I'm going to take the first plane here, well, maybe this one here version instead of that one, and I'm going to solve for x by substituting the 2 minus t and t in place of y and z. So here's the first plane. 2 minus t goes in place of y, and of course t in place of z. And so when we take the brackets off, we get negative 2 plus t, and so t and t add to 2t. So solve for x. When we add 2 to both sides, 1 and 2 add to 3, and of course this would be minus 2t on the right. So that's the x parametric equation. So the parametric equations of the line of intersection are x is equal to 3 minus t, y is equal to 2 minus t, and z equals t. So that's the equation of the line that these three planes intersect at. To determine a particular solution, which of course is again is just an example of a point that's on this line that would also be on all the planes, we just substitute any value 1 in for t. I chose 4, but if you wanted to use 0 or 1 or 2 or negative 6, wouldn't matter. So I put 4. So 3 minus 2 times 4, that's 8, so 3 minus 8 is negative 5. Putting 4 in place of t here, so 2 minus 4 is negative 2, and z would equal 4. So negative 5, negative 2, 4 is an example of a point that is on all of the planes. So that's the particular solution. And that's the end of the video.